Okay, so today we have three presenters. The first presenter will be Professor Sang-Won Su, and I think many of us know Sang-Won because he's a distinguished professor and have made tremendous contributions in the LCA field. And as many of you know, he actually won, numerous awards, including the Loudest Medal of Industrial Ecology, Leon TF Memorial Prize, Richard Stone Prize, and also a Lifetime LCA Leadership Award. And also, I think Dr. Su actually made a very important contribution to the global, climate research community, right? So he's a member of the United Nations Environmental Program and also the lead, coordinating lead author for the IPCC, and also serve on the technical group of GHG protocols. I think we all well familiar with those important stands and organizations. But some of you probably don't know is that someone is also the head of science at Watershed Technology, a company that actually trying to scale up and improve the way we do LCA. So that will be his presentation today. But unfortunately, due to the conflict of the schedule, someone would not be able to join us in person, but he actually made a recording so that I'm going to play the recording. And then again, I will collect the question at the end and forward to him. Okay, let me try to see if it works.
Hello, everyone. This is Sang-Won Su. I'm the head scientist of Watershed. Today, I will tell you more about the applications of AI in the field, the broader field of LCA at Watershed. And this is a collaboration with my colleagues who are listed in the screen here. So first, I will talk about the motivation and objectives and the two areas of application of AI that we will showcase today are Atlas and two reduction levers library. And I will talk about the future works and then conclusions and discussions. So in terms of the motivation, so 30 years after the emergence of LCA in the literature, we are still hearing more or less the same issues that we have heard 30 years ago. So the first one is that data is scarce. We hear this everywhere, right? And the two, LCA is not scalable. And third one is conducting LCA is costly. So the question here is that can AI be a conduit to overcome these limitations? So the objective today are a few folds. Let's say first, the question is whether use of AI can overcome some of these key obstacles. We want to, test this kind of hypothesis. And we want to do that by means of showcasing two applications of AI at Watershed Labs. And obviously, we haven't solved all the problems in the world in conducting life cycle assessment, but I hope that these two cases kind of give a glimpse of hope that, well, in some areas of these challenges can be resolved using the application of AI. And then finally, I hope that this is an opportunity to share ideas for future research and collaboration. So first about Atlas. This is about reliable and scalable mapping. So why we are talking about mapping? So first, let's talk about what is mapping. So on the right, this is based on the ISO standard on life cycle assessment. What you are seeing within the box here is the processes from which you can draw the primary data. However, these processes are using inputs from compressed air, compressor, basically inputs of compressed air from compressor, and they also use electricity, light fuel oil, natural gas, BOF gas, etc. These should come from somewhere else, and ideally, they should come from the primary data sources, the suppliers that are producing them. However, as many of you know, collecting those primary data is very costly and time consuming, and we have a lot of challenges in doing so. So in many cases, we are relying on secondary data sources, be them eco-invent like process LCA databases or input-output databases such as USCIO database or the CETA database. So this is the kind of the activity that almost all LCA practitioners are doing on a daily basis. However, there is virtually no literature about mapping. These are generally kind of a low-tech manual process, and there is no real theory or papers that are really talking about this mapping. However, in my opinion, mapping remains as the most time-consuming yet highly uncertain procedure. Virtually no papers are talking about uncertainties due to the incorrect mapping. So scaling LCA and carbon footprinting requires rapid and reliable mapping, mapping of bill of materials or the spend data. And today we'll focus on the spend data mapping. I want to mention an important prior literature on this area. So Bharathan, the co-organizer of this session, made a very pioneering work based on a vector similarity-based approach that achieved 75% matching precision on data set of 664 product. And another paper, Jane et al., was actually a conference paper, used a zero-shot and supervised fine-tuning on a data set of more than 2,000 financial ledger investment. However, to our best knowledge, there is no benchmark data set for systematic comparison of different modeling approaches, and that's what Atlas is about. So on the right, what you are seeing is the paper by Bharathan. It's called Flamingo. Many of you are familiar with that. And on the bottom, you can see the relationship between the predicted category versus the ground truth category, and first and true values you can see on the blue and orange dots respectively. So Atlas is, to our best knowledge, the first spend classification benchmark data set that includes 10,000 synthetic spend classifications spanning 9 macro industries and 8 countries. What we mean by synthetic spend description is this. So we deal with hundreds of world's largest companies at Watershed. Those actual spend descriptions are proprietary. We cannot reveal those actual spend descriptions by our customers. So we have to transform them into more synthetic spend description that is, in a way, that is definitely different from the actual spend description, but is actually very close to the actual spend description. And then the question is, how can we map that description to industry categories? So synthetic spend descriptions can be like video production expenses or payment and commercial pressure washers, for example. And then we want to map that to actual the industry classification, such as NAICS code, the North American Industry Classification Code. An Atlas dataset is available for free for academic purposes upon request. So if you are interested in taking a look at this database, let us know. And we want to showcase 4 baseline models that we developed and their performances for mapping the synthetic databases to industry classification categories. So these are some of the examples. So for example, synthetic spend description can be video production expenses, copywriting, and content creation. And then, well, BEA code, the Bureau of Economic Analysis industry code that is derived from the North American Industry Classification Code, can be advertising, public relations, and related services, BEA code of 541800. And similarly, if this description is system maintenance payment, commercial pressure washer, that can be mapped to non-residential maintenance, repair, etc., etc. So the structure and content of the Atlas database is that, well, on the vertical axis that you are seeing buying industries that spans from resources transformation to food and beverage infrastructure, financials, all the way to different services. And those buying industries spend categories includes raw materials, utilities, and construction, etc. The ones that you can see the dominant the composition of the spend items are services, especially some sectors such as financial sector and other service sectors dominate services for their spend items, but it also includes like finished goods as well as semi-finished goods, etc. So we tested four test models. These are all also based on AI-based test models. And we measured their performances and a number of different indicators. I will walk you through this test result. But these are just sample models, and obviously you can develop your own models, and using Atlas, you can test the accuracy and precision and other key indicators of your model. The first one that we tested was text embedding model, we call, and it's based on OpenAI's new embedding models published in January 2024. And the second one is a regression model based on normalized word frequency. This is logistic regression model. Third one is Anthropic's Claude 3.5 Sonnet with a two improvement that we made. One is a chain of thought prompting, and the second one is a meta prompting techniques. So these are the techniques that we have added to improve the Anthropic's Claude Sonnet. The last one is a few-shot LLM that is in-context learning with dynamic retrieval of 50 samples to train the prompt. So based on the line item in question, we basically dynamically retrieve 50 samples so that we can create the better prompting. So we use 5 different indicators to measure the performance of these models. The first 3 are the accuracy, whether it correctly predicted the right category, and the fourth one is the degree of fabrication. So if you're familiar with, for example, waste input output model, you may be familiar with the degree of fabrication, the concept of the degree of fabrication, which is basically is about where in the journey of raw materials all the way to the final product manufacturing does the process belong to, or materials or services belong to. So that is DOF, degree of fabrication. And the last one is the root mean square error, RMSE, of top 1 emissions factors. And that is a lower the better indicator. As you can see that the few-shot LLM showed the best performance in terms of the accuracies and also degree of fabrication, as well as the RMSE scores. So in this particular case, few-shot LLM is the best performing model that we have come up with. And obviously, you can create your own model and test it by yourself as well. So that was about Atlas database. And second showcase is the reduction lever library. As you know, even if we implement all the policies under the nationally determined contributions, we still have about 20 gigaton per year of CO2 equivalent greenhouse gas emission reduction gap that we need to close. And that's why the private sector's role in reducing greenhouse gas emissions is so important. However, the effective greenhouse gas emission strategy depends on industry and geography, and companies need the latest information on the reduction levers that actually work. However, to our best knowledge, there is no go-to reduction lever database available on what is being practiced out there. However, information itself is out there. Unfortunately, those information is dissolved in very text-heavy form, like in sustainability report, in PDF files, and climate disclosure platforms, and they are unstructured and less machine-friendly and text-heavy. So we aim to create a structured and timely database that includes feasibility of those emission reduction levers and the cost and reduction potential by sector and geography. So it takes a number of steps. I will not go into too much of details, and those steps and the details are available in a paper that will be published through the NeurIPS conference, and also they were presented during the workshop that Qingshi and Marathon will organize after the NeurIPS, so that you will be able to find that on the web in a few weeks of time. So the first one is to extract text and summarize actions. So on the right that you see some examples of a sustainability report. These are text-heavy form, and then we extract actions like what kind of actions are taken, and then second, how much of reduction was achieved by that, and then we put that into more structured format, and then we classify actions into emission sources, and that is the standardized source categories, emission source categories following the IPCC classification. And then we add feasibility and reduction potential information. There are some cases, I apologize for the noise. In many cases, those additional information is lacking. In that case, we use the supplementary data sources such as Exponential Roadmap Initiative and Project Drawdown Initiative to add those information. And finally, we determine the top emission sources and sectors, and then put that into more structured database like this, so that you can see, in which sector, what kind of top emission sources were out there, and what are the source contribution to the sector, and then what are the actions taken, and what were the dollar per ton of reduction, and what are the geographies associated with the data set. So those were the two cases that we wanted to share with you. We work on a number of other applications of AI to improve life cycle assessment and carbon accounting, but we weren't able to share some of those works, but hopefully in the future we can share more as our work progresses. And these are some of the future works. First, we want to expand our Atlas database toward more buying sectors and more spend categories, and also we want to include process LCA databases, which is currently not included in Atlas. One area that we identified as a potential improvement is the prompt engineering, and there are a lot of literature going around these days on prompt engineering, and this is one of the areas that we want to further improve the ways in which we apply AI for answering some of the questions. Third one is validating our result and models using actual company data. The proof is in the pudding. So can we use high quality manual mapping result for sampled mapping, estimated mapping results using the predictive models, and see whether they are correctly mapped under these estimation tools is one of the questions that we want to test with actual customer data set. Another one is whether the priority reduction actions that we have come up with are actually applicable in practice. So we want to run those kind of reduction actions with companies and see whether they also see that these are key emission reduction opportunities for them. So these are some of the future works. These are my last slides. So I think that we are beginning to see the potential of AI in addressing three major challenges. That is data scarcity, scalability, and cost. And we showcase two examples of our work. One is Atlas, and second one is Reduction Levels Library. And I hope that this gives a little bit of hope that we can probably address some of these problems with the help of AI, which I think is really exciting area of work. And I think that still the field is at its infancy, during which time I think the collaboration and learning from each other is especially important. So I hope that today's session provides the opportunity to learn from each other and hopefully create more collaboration opportunity. I thank you for your attention. I hope that you have a great session today. Bye.
Great. Thank you, Sang-Wan, and especially thank you for promoting our workshop. A lot of insightful content. I think we will have some discussion in the panel session. So let's move on to the next presenter, Dr. Avan Kumar, who is a postdoctoral scholar at Arizona State University. And Dr. Kumar is a chemical engineer by training, but he also has his expertise in a variety of machine learning, like deep learning, natural language processing field. And his recent work, I think, is trying to apply large language model and AI for extracting the information from unstructured sources for example, a life cycle assessment. So without further ado, I will pass it to Dr. Kumar, and we can actually see your screen in a full presenter mode. You're all ready to go.
Hi everyone, thank you, Professor, for nice introduction. So today I'm giving the talk on Sustain-GPT, which is basically leveraging the large language models potentials to extract the structured database from the unstructured and text resources to basically to get the lifecycle inventory. So I worked with my supervisor, that's Professor Bhavik Bakshi, and my co-author Amrita Sen. She is working in DAO now. So okay. So let's start with the motivation part. So as we all know, like we have the LCA tool, which gives the sustainability assessments. Okay, so it has the majorly four components. Okay, so it has the 4 stages: goals and scopes, life cycle inventory, impact assessment, interpretations. Okay, so among them, like the toughest part is the life cycle inventory, which is like need to have the data acquisition, system boundaries, and lots of other stuffs to need to define, and then we can get the life cycle inventory for the particular product. For that, we need to have the expertise. It's a time-taking process. If we do not need, basically, if we want to take the data from the commercial databases like 𝐒𝐞 or other resources, so we need to pay. Okay, so there is some lack of data like the emerging technologies, so that it's basically constraints us to do the LCA correctly for the emerging products or the technologies. To overcome these limitations, so here we are integrating the large language models with scientific literatures to develop a chatbot that will assist the LCA practitioners with the LCI data. Okay, so as I talk with the large language models, so let's talk about like what is the large language model is actually. So large language model is a deep learning model which is based on the transformer architecture, as we can see on left hand side. So it is combined with the encoders, the first left part, and then right part is the encoder part. So which is like the breakthrough in 2017 by Wang et al. After that we had lots of transformer based, or they utilized the transformer architectures to get their job done. So in 2018, so the BERT was the one of the famous one, and then we had the couple of models like GPT-2, GPT-3, Lambda, and instruction GPTs. So here are on the right hand side, so we have couple of very famous large language models like ChatGPT, so everybody is using it for different purposes. So the Llama is also released by the Meta, and then we had the Gemini, which is launched by the Google. So okay, so we have couple of models, the open source models. So researchers have developed some frameworks. They utilize those sources to estimate, to assist the LCA completely. So here are some literatures they published recently. So the first one is basically AutoCFC PCF. Basically, it gives the carbon footprint for the products. It's basically completely automated. They use the open source models, and then there are a couple of other tools. They utilize the large language models to do the LCA framework. So at last we have 3 papers where they discussed about the scope of LLMs in LCA. So one of the paper is like the citation 8, which is Professor Tu has released in Environmental Science and Technologies. So what has not done yet? So it's basically like there is no paper. They have trained the model based on the specific data set, or if I talk about the specific area, so the chemical industries. So what we are proposing here, so we are retraining the LLM from like pre-training and then fine-tuning to get the impact category data or the LCA data set together. Okay, so what's the difference between open source LLM or customized LLM? So as we can see here on left-hand side, so the user will query like the LCA query. So the open source will give the responses. So here we have 2 open source models, Llama 2 or ChatGPT. So the model will give the response, definitely, but the low accuracy or the precisions, it may be the major drawback. And then we have the hallucinated responses, and the model has the limited resources. Basically, it's not up to mark. So we are adapting the retraining part. So to retrain the weights of the models to with the domain knowledge to get the retrained models. So based on that, if we are going to ask the questions related to LCI, so we'll have most likely the high accuracy, no hallucinations, or it's up to mark literatures in their databases. Okay, so the 2 questions come to mind, like which large language models are we going to use, or which type of data will be used for my study? So answer is here like, okay, so the first one, large language model, so which is like recent or most powerful model, that is Llama 2, which is released in July 2023 by the Meta AI. Okay, if somebody want to learn more about it, so they can scan the QR code. Okay, so apart from that, like type of the data sets, so the scientific literatures we are going to tackle, which is unstructured data. So the unstructured data is like 90% all over the world. So which is like a huge amount, or it hides lots of informations in it. So we are going to unfold such informations to get to basically to get the specific task done, like LCI inventory. Okay, so here we have the preliminary workflow, what we are going to do, or like how we are going to use the scientific literatures or the Llama model. So scientific literatures based on the methanol. So this complete study will be based on the methanol LCA study. So we are trying to get the life cycle inventory data for the methanol productions. So that literatures will be used to pre-train the model. So we'll get the retrained model. So parallelly, we have the question answering data set. So that question answering data set will help us to get the model fine-tuned for a specific task, like question answering task. So then we get the Sustain-GPT. So Sustain-GPT will help us to achieve these 3 major goals. Like it will retrieve the range of the input output streams values or impacts. So it will act as a knowledge extractor or like a chatbot. So that will help the LCA practitioners to basically to get their job done. And then we'll try to get the synthesize the data for the emerging technologies or the chemicals. Okay, so here is the technical framework. So we have majorly 5 steps: the data extractions, data annotations, pre-training, and then fine-tuning part where we'll get the question answering module. And then at last, we'll test the Sustain-GPT trained model. Okay, so let's start with the data extraction. So here we are going to extract the data from the LCA literature database. So where we using the API key with some relevant keywords. So these 3 set of informations will give us abstracts along with these full text. So needs the full text, needs the XML custom XML parsings, so we can get the full text of the articles, which is like a relevant articles completely, because we are using the relevant keywords. And on those extracted data or relevant data will use to pre-train the model. So what's the meaning of pre-training? Is basically like large language models, we need to update their base weights. Okay, so we are updating entire weights of the Llama 2 by incorporating domain knowledge of methanol. So as we can see in the middle, like, okay, so Llama 2 is taken from the Llama resources, LLM resource, and then we are feeding the knowledge or the literatures to update their weights. So at the end, we'll get the custom retrained LLM model, which is Llama 2. So, okay, so we need to see like how well the model is trained. So for that, we have the learning curve. So where we can see, so the red line is representing the training loss or the validation loss for the blue line. Okay, so here are some technical details with respect to the learning curve. So for updating the weights, so we need a computational resources. So we use the ASU, Arizona State University supercomputer facility. So basically it took around 82 1 week at 82 GB of NVIDIA GPU card. And then we are going to do the data annotation part. So here is the like why we need a data annotation. So to do the fine tuning, we need a data set. Okay, so we had the relevant articles, that relevant articles processed by the human experts. So that person created the question answering 1000 plus questions and answers. Those are related to the life cycle, like life cycle inventory, recyclability, environmental impacts, 𝐒𝐫𝐠𝐚𝐧, such categories. Okay, and now we'll do the fine tuning part. So we have the retrained model Llama 2. We created the data, question answering data. So we are feeding like just fine tuning the model to perform the question answering task specifically. So after fine tuning the model, so we get the Sustain-GPT, so which will help the users to get the answers done. To check the performance of this Sustain-GPT or fine-tuning step, so we are using the metric, that is the F1 score metric, so which help us to evaluate the performance overall. So based on our study or like based on our data set, so we got the 0.92 F1 score, which basically tells us, okay, so the responses generated by the model, trained model, which is similar to 92% of the actual responses. At last, we evaluate the Sustain-GPT with the qualitative or the quantitative analysis both. So here is the quantitative analysis. So we ask the question related to global warming potential to particularly one case, 1 kg of methanol from natural gas to 4 cradle to gate cases. Okay, so we ask the question, so we get the response. So as we can see here, the response is 1.336 kg of CO2 equivalent needed for producing 1 kg of methanol. Okay, so to get the uncertainty of the value of GWP, so we ask the same question multiple times to Sustain-GPT. It gives multiple responses. As the literatures, they had different assumptions, or based on that they get the different values. So as we can see on the right hand side, so we have the error bar plot, so which gives you a very good visual spectrum, like what the value of for the GWP for 1 kg of methanol. So that thing we validated with the UC LCA database, which is open source database, so which is close to our extracted results. So similarly, we asked the question for the energy demand for 1 kg. So on the left hand side, we can see the error bar. So it's a range particularly. So we validated with the published database, which is like in Journal of Power and Energy Systems. So which tells us, okay, so 10.62 kilowatt per hour to 13.3 kg per hour is the range for methanol production of 1 kg. Okay, and after that we try to get the complete LCA data set for particularly one stage, which is the production of from raw material to methanol. Okay, so this is a process LCA data set. So we verified our extracted response, as we can see in the middle column. Okay, so which is like validated with the other resources like the citations 1 and 2. So the outcome of the Sustain-GPT is like has the range, but it's validating the actual values, as we can see here. After the quantitative analysis, so we did the qualitative analysis. So we asked the couple of questions. So the first question based on the hotspot analysis. So we trying to get the hotspot for the process or the life cycle of the product. So we asked the question GWP hotspot in methanol from natural gas life cycle. So the Sustain-GPT model is giving the numerical informations or qualitative informations along with the qualitative informations. So as it just tell us, okay, so the natural gas productions like 76.6% of total GWP generated during the natural gas production stage. Okay, so which is like a hotspot. So same question we asked with the ChatGPT, the current version. So the response is here. So it seems like a qualitative completely. It's not completely informatic or no numerical information present in it. So we can say, okay, so Sustain-GPT is giving more informatic information. So afterwards, I asked the one different question. So what is the carbon conversion for methanol productions for electrochemical processes? So it giving us a exact number, okay, so 70.5%. When I asked the same question to ChatGPT, giving a broader range. So it's like a complete range, but it's not specifying like what's the actual value is. So that 70.5% given by the Sustain-GPT is based on our latest literatures we fed it to the model. Okay, so at the last slide, we had the conclusions and future scopes. So we developed the Sustain-GPT for LCA practitioners for a specific task now for methanols, and then the train model giving the quantitative and qualitative informations together. So the responses are relevant based on as we use the scientific literatures from the LCA database. So future work, we going to include the source of the responses generated by the models for user validations and additional information. So we also will target to expansion of databases by including the CS or for the broader scientific coverage or other chemical products except the methanols. I acknowledge the funding agencies or my ASU supercomputer soul, or here are the QR codes for my research lab or my personal LinkedIn profile. If somebody wants to explore, they can explore. Oh yeah, thank you for your attention.
Thank you, Dr. Kumar. Very, very good presentation. Very clear about the the methodology, and it's very exciting to see the the effectiveness of your customized large language model. And certainly we can. Hopefully, we still have time for the panel discussion. There are a lot of interesting things we can discuss about. Thank you very much.
Yes.
Yeah, and we will move on to our last speaker, Dr. Nan Li. He is an associate professor at School of Environment at Tsinghua University, China, and also the deputy director of the Institute of Environmental Sustainability and the Environmental AI Research Center. And his research focuses on development of scalable data infrastructure for environmental information systems and integration of AI. If you check Dr. Li's GitHub repository, he has pages of very useful code for really kind of do a scalable LCA using AI-driven, different software packages. And today, Dr. Li will actually give us a talk on his insights on how we can actually build the next generation of LCA in a way that is AI native. So without further ado, the floor is yours, Dr. Li.
Okay, thank you, Qingshi. Hello everyone. Today I'm going to talk about the AI native pathways to the next generation of LCA. My name is Nan Li. Through this presentation, I will introduce the possibilities that how AI may transform the LCA. But today's presentation might seem a little technical, but don't worry, it's actually much easier than it sounds. I promise no one's going to need a PhD in computer science to understand this. Well, except me, maybe. Well, here's the overview of what I will cover today. I will start with some background on current challenges in LCA and where there is a need for AI innovation. Then I will discuss our early stage attempts at integrating AI into LCA processes. Finally, we will try to explore the pathways to a truly AI native LCA transformation. Around the world, there are both voluntary and mandatory drivers pushing for low carbon, green and sustainable products. On the voluntary side, we can see the companies like Mercedes, BMW, H&M, Apple, Amazon committing to decarbonize in their own supply chains. On the regulatory side, policies like the EU's Fit for the 50/50 and 55 and the carbon border adjustment mechanism, the CBAM, are setting stricter requirements. LCA is one of the key tools for addressing the challenges for decarbonization. Although LCA offers valuable insights, it's not a medical bullet for carbon footprint analysis. But the process is both expensive and time-consuming. Well, however, implementing LCA involves several challenges. We have to do the on-site investigation, we have to do the laboratory tests, we have the surveys, we have the literature reviews. Well, all of these require a significant time and resources. So such complexities highlights the needs for the innovations to make LCA more accessible and efficient. Well, let's continue with the section 2, where I will share some of our early stage attempts in integrating AI with LCA. Well, this will set the foundation for understanding the pathways to an AI native approach in LCA. Well, one of the major advantages of AI in LCA is its ability to handle complexity. Well, AI can filter out uninteresting complexities, allowing us to only focus on the valuable insights without getting distracted by unnecessary details. As you can see in this photo, I took this in the GitHub Universe conference last month in San Francisco, but the AI reduces the cognitive load by providing instant feedback and simplifying the workflows, empowering us to make quicker, more informed decisions. But basically, the AI transformed the LCA by managing the data heavy process more effectively, but making it possible to conduct in-depth LCA without overloading human beings like us. And in other words, if one can use the AI as his own tool, he will become or she will become an AI-powered Superman or Superwoman. Well, we have our first trial of the data curation of the image. As you can see, the left part is the image from the PDF. The right part is we're using ChatGPT multimodal to read this flow chart. I have to admit, the most of the time. Well, here's the example. The left part is the table from the PDF file. The right part is the ChatGPT multimodal read the table and transform it into plain text in the HTML format. That stands for the hypertext markup language. That means the AI understand what each cell's value actually means. Then the second phase of the trial is all about data mapping. I think it's about matching data. For example, carbon dioxide has its unique CAS number, but people may call it by different names in different languages. Well, with the help of LLMs, we can use our own native language and the different ways of expressing ourselves to match the data. We can use the CO2, even use the 二氧化碳 in Chinese to retrieve the flows. Well, the third trial is we have done a complete AI-driven LCA modeling. Well, it's the LCA of Chinese aluminum ingot production based on the LLM agent. We conducted 3 modeling approaches at the same time. The first one is the automatic modeling by LCA software, traditional LCA software. The second is done by the human experts. The third is done by the LLM agent. Well, this LCA model covering the entire process from the bauxite binding to the ingot casting, along with supporting stages like coke and anode production. As you can say, the AI can trace the process from the tier 1 all the way up to the tier 4. The first time I saw this, I was astonished myself. I can't believe it. But what about the result? Well, the vertical axis is the normalized value. Well, the horizontal axis is the different kinds of the environmental impacts. The pink dots stand for the result by the human experts, while the blue stand for the LLM agent. Well, blue plus pink is purple. As we can say, there are many purple dots and curves in the figure. Well, that means the AI agents can reach a level comparable to human experts. But on the contrary, there is a significant difference in the gray ones. That is done by the auto-link functionalities of the traditional LCA software. But the trials I have just mentioned provide us with the confidence to explore our unique pathways to the AI native LCA. But first, I'd like to start with discussing what is AI native. But nowadays, many companies saying that they are having AI native solutions. Is that truly the case? Well, the answer is likely no. Most of them only have replaced existing component with AI-based component, or they add a new AI-based component, or they add an AI-based control to a legacy component. What is AI native? That is where all the components potentially use AI in and among each other. That means without AI, especially the generative AI, the solution doesn't exist. But that is the very definition of our definition of the AI native. So what is our pathway to the AI native LCA? We call it the Tiangong suite. Well, the 𝐻𝐤𝐽 is a name from a Chinese ancient book, which is published in the Ming Dynasty. The book features detailed illustrations that are valuable for us in understanding many early Chinese industrial processes. But the Tiangong suite is composed of 4 parts: a knowledge base, AI optimized LCA database, multi-level agent, and of course, AI native LCA platform, the software. Well, referring to the knowledge base, instead of using ChatGPT, here we're using open source transformed models from Hugging Face. We have the automatic declaration functionalities of figure screen, the parsing and analyzing tables, and the paragraph merging. But besides the metadata, we have also built full text search for keyword matching and vectors for similarity search. And we have realized that a technique called hybrid search is absolutely essential in our knowledge base. Well, the keyword search in the left part is more like what we use on Google every day. It gives back results with exact matches. Well, the vector search is more complicated. It's a method that uses mathematical vectors to represent the data, allowing the search system to find them are similar in the meaning, of course, regardless of languages, other than just matching the exact words. But it's useful to finding relevant results, even if they don't contain the exact search terms. So here's an example. Well, the original query is the 2020's recycled aluminum in southern China, Chinese cities. Well, we can use the original query to do the semantic search in the vector database. And then the LLM can generate the query both in Chinese and English, the phrases like the recycled aluminum, the southern Chinese cities, the 2020, the life cycle analysis, etc. Well, this actually solves a big problem. Often we know a certain technical terms in one language, but are not familiar with what they are commonly expressed in other languages. Well, direct translation doesn't work here, right? So we often cannot find the information we are looking for. But before the LLM came along, this thing used to frustrated me every single day. Then we have already established a huge knowledge base Well, it covers the categories of the research papers, reports, patterns, the standards, books, and the ESG reports. It's more than 70 billion tokens times 2. One is for the full text, the other is for the vectors. But the second part is the Tiangong LCA database. Well, it's a community-driven project by our university with more than 40 principal investigators and more than 200 researchers. Well, it's an open, transparent LCA background database. And now we have more than 40,000 unit processes in our databases. But our database is 100% aligned with the EF 3.1 reference packages and 100% IOCD format compatible. And also we developed a data structure for the two-way conversion for both human and AI. And all our data is open, can be open accessed on the GitHub. And everyone can watch what have we done to our data. Well, thanks to the LCD format compatible features, and now we are the third biggest database in the portal of the United Nations GLAD network, and we are the biggest open and free database in GLAD, and we have already set our own Tiangong LCDN node with the soda for LCA. The part 3 is the multi-level agent system. You can see the 3 levels, 3 layers. The first layer, the basic functions that cannot be divided anymore, like the literature searching, the pattern searching, the report searching, the content verification, etc. And the second layer is the unit agents. The agent use the basic functions. The third level is the multi-agent orchestrations. There are many different agents here in a one-way graph. And all the 3 layers are deployed on the industrial level cloud native environment in the AWS. Well, for the first basic function, it's very easy. You can just send your request and the service will return the knowledge-based search result. And all the basic functions are global accessible, and including the LCA flow data, hybrid search, and services. Well, this slide is very interesting. Well, this slide introduced a graph-based agent system by structuring the process as a cyclic graph. I mean, the blue part, we can control and adjust each step by defining nodes and conditional edges. Well, the system combines the retrieval augmented generation, aka RAG, with self-reflection, allowing it to retrieve, analyze, and generate answers time and time again until it reaches a satisfied response. Well, this agentic approach makes the process flexible and adaptable, ensuring more accurate and context-aware outputs. Well, this is a typical AI native LCA data extraction workflow. As you can see, there are many different agents playing different roles. We can see the agents for extracting system boundaries, agents for extracting process time period, and finally we have agents for converting data into ILCD format. Well, that means every agent must follow the orchestrated workflows. You can never turn back. It's called a directed cyclic graph, aka DAG. Well, here's an example of how a parallel sub-orchestration works. We did this last night, but basically we only have 3 steps. The first is the retrieving. The second is analyzing, is what is demonstration in this video. And the third is the converting into the structured table. Yeah, Excel. So we have extracted more than 100 reliable records from 70 different documents in 90 seconds. Well, because it's paralleled, we can do 700, even 7,000 different documents in the same time. So we are very excited about this. Well, as for the part 4, is the LCA platform, the software. We have full functions of the data management, modeling, calculation, verification. And also I have mentioned the innovative data structures and also the AI native, like the intelligent data search, the recommendation engine, the copilot, agentic automation is on the way, maybe in a couple of months. Well, this is our technical architecture. You can see we have a lot of layers like the LM layers, knowledge layers, AI components, orchestration layers, and all the projects are open sourced in MIT license. That means you can use all the codes even in your commercial activities. Well, special thanks to the GitHub Copilot, I have opened more than 40 new open source AI for Sustain-GPT projects since the year 2023. And I'm also a contributor and reviewer of the OpenAI ChatGPT plugins and LangChain framework. Well, finally, the takeaways. The first thing I would mention is the LCA is a time-consuming and labor-intensive process, often requiring practical compromises. The second is LCA needs high-quality, traceable data and modeling. The third is AI-native LCA is a foreseeable future. But the last, I think, is the most important, that the infrastructure matters. Well, even a best cook cannot prepare a meal without ingredients, right? You cannot make something out of nothing. So infrastructures such as a human and AI accessible LCA data structure, an accurate, extensive and detailed knowledge base, and a flexible agentic framework are essential prerequisites for this realization. Well, that's all for today. Thank you very much.
Thank you very much, Dr. Lee. I think you realize your promise saying that you don't really need a PhD in computer science to actually understand all these kind of very intuitive examples and very exciting. And I guess we don't really have time for questions, so I want to do a quick like a summary of at least my takeaways. So I will also invite Dr. Kumar back. So is that I feel like this is really an exciting field, right? So we see 3 different presentations and actually all have different takes on solving this scalability problem of LCA, right? So using, for example, a customized large language model, or use a agentic flow with customized knowledge base, and also like for example, someone's study is actually on how can we improve the mapping, which is also something we're actually looking into as well. So I think all these are very, very exciting research work, and I think this field will be like attracting more and more people and probably research funding, and we will see a lot of publications in this field probably in the near future. So yeah, I will highly encourage our audience, if you're interested in this particular field, reach out to our presenters and really just kind of sign up for the ISIE newsletter. You will, I'm pretty sure you will see a lot of this kind of publications publishing JIE and other, prestigious journals. So I think we are right on the mark. And thank you again for attending this session. And I hope you have a wonderful day or evening, and hope to see you in person in the future ISIE events, such as the ISIE 2025 conference in Singapore. Have a good one.